Welcome to Opportunity Crude Management Seminar Series, an informative look at crude processing challenges. Disclaimers. The purpose of the OCMS series is to provide refiners with the latest information in processing opportunity or price-advantaged crudes, such as heavy sour oil, oil sand bitumen, light tight oil, and highly acidic crudes so that they can make better decisions in light of a volatile oil market. Opportunity Crude Management Seminar Series, Video Number 6, A Lot of Problems, Fouling and Corrosion, Part 1, Fouling. As mentioned in our previous videos, there have been multiple disputes between oil sellers and refiners over crude quality and blending practices. Refiners must take special precautions to avoid crude fouling. Crude fouling has been associated with operational and energy efficiency losses, costly expenditures to clean up equipment such as heat exchangers, and missed productions due to required shutdowns. According to the U.S. Department of Energy, fouling costs U.S. refineries over $2 billion a year. In this video, we will discuss the causes of crude fouling and options available to control fouling. The second part of this series focusing on corrosion will be shown in January. In today's video, we will discuss the sources of crude fouling, which include certain crude contaminants and properties. The role of the desalter as a first line of defense in preventing fouling will be highlighted. We will also examine when fouling occurs downstream of the desalter in other parts of the refinery. We will then focus on the causes and solutions to fouling from light tight oil as well as strategies in processing these crudes. Finally, we will discuss the benefits of chemical additives and commercial options available to predict, detect, and mitigate fouling. Navigate oil market uncertainty and supply disruption in refining at the 6th Opportunity Crudes Conference in Houston, Texas in the U.S. from October 22 to the 24th, 2018. The theme of the conference is Crude Disruptors, Accelerating Changes in Global Refining. Higher oil output and refining price advantage. Domestic light tight oil has benefited international oil majors and U.S. independent refiners in the first quarter, respectively, according to just released earning results. Unfortunately, the good news will end soon as the oil market is going to enter an uncertain time since the price rout in mid-2014. A dark cloud is forming as driven by two formidable forces, geopolitical risks and changing supply-demand fundamentals. Change is not new in the refining world, but disruption of crude sources could significantly upset overall refinery operations in terms of crude management, processing, and product quality and volume. Our attendees will learn from conference speakers and network with colleagues on how refiners can navigate present market uncertainty and crude supply disruption by devising better business strategies, finding ways to increase operational flexibility, and adopting new technologies to turn challenges into opportunities. As in our previous meetings, this conference is expected to be highly productive and rewarding because of excellent speakers, timely theme, well-organized agenda, and stimulating atmosphere to encourage exchange of ideas. 5 topical sessions in 2.5 days include: Session 1, Global Oil Market Outlooks, Geopolitics, U.S. Pro-Export Policy, OPEC Strategies, Peak Demand. Session 2, Challenges and Opportunities in Oil Trading, Exports, Imports and Infrastructure Logistics. Session 3, Crude Contaminants, Incompatibility, Blending Strategies Amid Changing Feedstocks. Session 4, Flexibility of Light Tight Oil Processing and Bottoms Upgrading to Make Products in Demand. Session 5, Big Data Analytics and Emerging Adoption of Internet of Things in Crude Selection, Management, and Refining. In this celebrated biennial meeting, you will meet colleagues from many companies around the world. The Opportunity Crudes meeting from October 22 to the morning of October 24 is coordinated with Crude Oil Quality Association's fall meeting, which will be held on October 24 and October 25 to benefit from synergy in serving our upstream, midstream, and downstream colleagues. To save up to $300 before June 1, register today by visiting opportunitycrudes.com/Houston 2018. Here is a preliminary agenda for the 6th Opportunity Crudes Conference. refiners must be aware of crudes that are more prone to fouling. Specific crude properties and contaminants increase the likelihood of fouling. There are also certain practices and conditions that also lead to fouling. Shale crudes, which are inexpensive and can provide better margins, have high wax content that can form an asphaltenic sludge when mixed with heavier crudes. Also, amines used to reduce hydrogen sulfide content can cause both fouling and corrosion. As discussed in Seminar Number 3 on crude selection, some crude properties and contaminants are known to cause fouling in refineries, as shown in the table. These properties include asphaltene content, compatibility, paraffin content, sediment content, TEN or total acid number, and contaminants. Asphaltenes, which make up the most polar and aromatic fraction of crude, have been known to cause fouling when unstable. As discussed in Video 5, Soluble Solutions Colloidal Dispersion Solution Model states that in stable crudes, asphaltenes are generally dispersed by resins, and later dissolved by small ring aromatics, then by saturates or paraffins. When this process occurs, asphaltene instability and subsequent fouling do not occur. The figure on the right shows the colloidal dispersion solution model. The resins in petroleum normally associate with the asphaltenes and act to peptize them. Key to oil stability is the ratio of resin to asphaltene. If the resin to asphaltene ratio is too low, not enough resins are present to peptize the asphaltenes and the molecules may precipitate out of the solution and present a fouling problem. Excess heat can break down the resin to asphaltene complex into a pre-coke species, which can occur in heat exchangers. This occurrence involves the polar, paracondensed asphaltenic species and may occur regardless of the compatibility of the crude blend. That is to say, suspended and soluble asphaltene constituents can become insoluble and foul heat transfer surfaces. However, the ability of resins to stabilize asphaltenes varies among crudes. Typically, heavy crudes with a higher resin to asphaltene ratio have less asphaltene instability issues compared to lighter crudes. While resins stabilize asphaltenes, the relationship between the two components is rather complex. Resins with strong self-interaction tend to cause asphaltene destabilization. Other components have been shown to influence asphaltene flocculation. According to one study, naphthenic acids delay the onset of asphaltene flocculation caused by the addition of N-heptane. High amounts of saturates or paraffins have been shown to encourage asphaltene precipitation. This occurrence, however, is dependent on the size or carbon number of the paraffins. Asphaltene instability is becoming an increasing concern due to strong interest in refining blends of paraffinic tight oils with asphaltenic dumbbell crudes. Because of this, asphaltene flocculation remains an active area of research. The blending of incompatible crudes to create a so-called dumbbell blend may lead to numerous problems in the refinery. These incompatible blends often cause asphaltene instability, which leads to fouling and processing difficulties that reduce the benefits of purchasing opportunity crudes. Asphaltene instability from incompatible crudes can cause extensive fouling in the crude preheat train. This will result in decreased energy efficiency, increased CO2 emissions, and increased frequency where heat exchangers need to be cleaned, and, in a worst-case scenario, reduced crude throughput leading to significant financial losses. As previously highlighted in video number 5, we are not compatible. Selecting compatible crudes is very important as fouling is a serious consequence from crude incompatibility. Light tight oil has significant levels of paraffinic hydrocarbons, which can undergo cracking to form polynuclear aromatics or PNAs and coke. It is reported that fouling rates can increase by 50 to 600% if the furnace outlet temperature rises 10 to 40 degrees Fahrenheit or 5.5 to 22.2 degrees Celsius. This causes problems such as the formation of sludges, solids, and waxes in crude storage tanks and lines, which include the lines utilized to transfer the crude out of tankage to the CDU. PNAs can also form from the wax of shale crudes. This negatively impacts overall refinery operation and profitability. The blending of paraffinic crudes with asphaltenic crudes promotes stable emulsions in the desalter and fouling in processing equipment. One crude high in paraffin content is waxy crude from Utah's Uinta Basin in the United States. Acidic crudes often contain calcium and other divalent metals in the form of naphthanates, which originate from the production water under conditions of alkaline pH. These naphthanates are soluble in organic media and thus can be carried downstream of production. In the refinery, they can precipitate, causing fouling issues such as desalter emulsion stabilization and fouling in the CDU preheat exchanger and heater tubes. When calcium naphthanates increase oil conductivity and decrease desalter voltage, this increases the fouling potential in the preheat train, which can lead to carryover of water into the atmospheric distillation unit. Certain contaminants in crude oils cause fouling in refinery equipment. Filterable solids, in particular organic solids and asphaltenes, contribute to heater fouling. As a general rule of thumb, 20 to 40 pounds of solids per barrel of oil or more will cause increased furnace fouling. The relationship between solids removal in the crude desalter and preheat train and furnace fouling was discussed at a past U.S.'s National Petroleum Refiner Association or NPRA Q&A session. The filterable solids content of the incoming feed should be monitored, especially when processing heavy opportunity crude, which are known to carry metals, clay, and iron oxides, to alert the refinery of potential upsets and allow the adjustment of desalter operations such as mix valve delta P and chemical treatment dosage. Asphaltene stability can also be screened for potential upsets. The liberal use of sodium hydroxide can also increase fouling. Nitrogen, which is usually at less than 0.1 weight% in crude and often concentrates in the heavier product fractions and residues, causes fouling in the main column overhead. Organic chlorides, which usually result from contamination from tankers, barges, dumping into pipelines, and refinery slops, cause fouling the crude tower. Scale inhibitors, emulsion breakers and other upstream additives containing phosphorus are causing problems. With respect to fracking fluids, those are limited to Western Canadian light fields where the geology is clay-based. In the lower 48 it is all carbonaceous for the most part and there are no phosphorus-based frac fluids being applied, yet there is severe consistent phosphorus fouling in some of the West Texas refineries according to Sam Lordo of Nalco Champion. Our previous seminars, What's in Your Crudes? Parts 1 and 2 covered common non-metal and metal contaminants and discussed analytical methods and commercial analyzers that could detect some of these contaminants. Studies at the Tulsa Joint Industry Project indicate that there is a direct correlation between fouling rates and the amount of metals. While light tight oil tend to have high metals content from fracking fluids, metals are also commonly found in both heavy and light crude oils in various amounts and are present either as inorganic salts, such as chlorides of sodium and magnesium, or as organometallic compounds, such as nickel and vanadium porphyrins. The table on the right displays average metal contents for crude samples of both Bakken and Eagle Ford shale formations in the U.S. In addition to crude characteristics, there are other reasons why crude fouling occurs. The practice of adding slops to the crudes being processed and the exposure of crudes to high skin temperatures or heat fluxes can lead to fouling problems. Increased light ends in the crude feed have a possibility of premature vaporization upstream of the desalter and the crude unit heaters. Higher vaporization can result in settling of solids on heat transfer surfaces. This can be prevented by the addition of an atmospheric pre-flash. While this practice can reduce pressure drop and prevent premature vaporization and fouling by asphaltenes in the crude unit heat exchangers, it can decrease overall unit yields as well. Here is our sponsor's experience. OCMS Seminar 1 discussed crude column fouling resulting from addition of phosphate esters during crude production that break down in the crude column. Crude column fouling can also occur from thermally unstable phosphate esters used as naphthenic acid corrosion inhibitors. The pictures shown are from a column that was using such a product. Any corrosion inhibitor containing phosphorus is subject to thermal degradation that can result in fouling. Tensient is a breakthrough in corrosion science that allows for safe and reliable refining of high-tan opportunity crudes. Reduced risk of phosphorus fouling and more effective passivation and ongoing corrosion protection can be achieved with up to 80% less phosphorus than competitor HTCI products. Tensient is different than any other commercial phosphate corrosion inhibitor. It is an ethoxylated triester with unprecedented oil solubility, thermal stability, and is non-acidic. Tensient reduces risk of phosphorus fouling and increases corrosion protection with up to 80% less phosphorus than competitor products. Tensient is making it easier for refiners to use more high-tan crudes. In the refinery, the desalter plays an important role in controlling fouling and corrosion by removing contaminants such as chlorides and amines. However, this process is affected by numerous crude characteristics, including water content, amine salts, chlorides, crude conductivity, calcium naphthanates, interfacial tension, and solids or sediment content. Both inorganic and organic solids can create a rag layer, which is a stable emulsion of oil, water, and solids that inhibit mass transport of oil, water, and solids at the interface, thereby reducing desalter efficiency and increasing fouling downstream. According to Dorf et al., there are over 30 patent applications on the subject from 2014 to 2017, and half of the patents come from refiners. There are crudes with specific properties that may cause fouling and emulsions in desalted crude. Heavy Canadian crudes with high levels of amines, solids, and hydrogen sulfide content tend to be problematic. Tramp amines from triazine hydrogen sulfide scavengers can cause emulsion stabilization. Also, filterable solids, which can be present in amounts of up to 300 pounds per 1,000 barrel, can interfere with emulsion control and accelerate fouling in the preheat train. Such difficult crudes often require a large desalter unit or specially tailored chemicals during desalting. Here is our sponsor's experience. Opportunity crudes may increase the rate of fouling because they contain a higher level of contaminants that are more difficult to remove. Dorf et al. Has invented two new desalter chemistries to supplement the emulsion breaker: reactive adjunct and amine removal agent. Reactive adjunct is a new class of chemistry that reacts with certain contaminants that are antagonistic to emulsion breaking, such as amines, ammonia, and metals. More efficient contaminant removal increases the speed of emulsion breaking, reducing rag layer. Rag layer reduction is a critical variable that increases desalter efficiency. The amine removal agent reduces corrosion risk in crude column overhead by breaking the amine cycle without the safety risks of adding acid. In general, CDU fouling is due to heat, vaporization, reactions of metal and asphaltene components to form coke, and deposits of contaminants and additives. Caustic used to prevent corrosion in the crude tower overhead can add sodium and result in fouling. Sodium is also known to cause fouling in the coker furnace. A rule of thumb is to limit sodium to less than 10 to 20 parts per million in coker feed by operating a desalter efficiently. Refiners must watch for fouling in the CDU cold section preheat exchanger downstream of the desalter, which normally does not occur when processing conventional crudes but may occur when paraffinic tight oils are in the crude mix. Crude-related fouling occurring in other units such as FCCUs will be discussed in subsequent seminars on bottom-of-the-barrel upgrading and shale and tight oil processing. According to a diagram from Nalco Champion's presentation Strategies for Mitigating Fouling in Refineries Processing LTO, there are several regions in the crude unit that may experience issues when fouling occurs from processing light tight oil. While refiners can use anti-foulants to mitigate these issues in all these regions, specific measures may also be needed in each section of the crude unit. In the cold preheat train, where waxes and solids may form, a water wash along with cleaning and degassing should be performed. In the hot preheat train, to mitigate solids formation and desalter carryover, Desalter optimization and the use of chemicals along with cleaning and degassing should be done. Refiners should perform cleaning and degassing as well as improve velocity in the pre-flash tower to prevent problems with asphaltenes, solids, and polycyclic aromatics. To reduce asphaltenes, solids, and polycyclic aromatic hydrocarbons in the atmospheric furnace, refiners must also improve velocity, exit temperature, and press balance. In the atmospheric tower, measures such as using salt dispersants and caustic, acidification, cleaning and degassing, and improving velocity can mitigate problems with amine salts, phosphorus, asphaltenes, solids and polycyclic aromatics. Finally, for problems with asphaltenes, solids, and polycyclic aromatics in the vacuum furnace, the solutions are improving velocity and degassing and cleaning. Increasing processing of light tight oil in the U.S. and other parts of the world has raised experiences in dealing with fouling problems of this unconventional oil as presented by Nalco Champion. The following table shows the causes of operational and mechanical fouling when processing light tight oil and solutions to these fouling issues. Some of these mechanical and operational causes are also applicable to other opportunity crudes such as heavy grades. Because the fouling mechanism is refinery-specific, it is recommended refiners to take a three-step strategy to resolve fouling problems. 1. Analysis of the fouling deposits, for example, identifying and quantifying elemental components. 2. Identification of precursors and stream characterization such as crude properties and contaminants. And 3. Fouling monitoring, such as in heat transfer and furnace testing using techniques such as ASTM D4807 for filterable solids and ASTM D7157 for crude intrinsic stability, simulation, and chemical additive selection as well as economic evaluation. Finally, refiners can also use chemical additive options such as desalter solids removal aids, dispersants, coke suppressants, and others. In order for refiners to handle crudes they may not normally be able to process, additives and additional techniques are required to prevent fouling issues. When these additives reduce problems in refinery operations, economic benefits are realized. Crudes supplied to storage tanks in a transportation system handling heavy asphaltenic crudes and light paraffinic oils often require pretreatment to break emulsions and disperse waxes. Additives are also used to reduce heat exchanger fouling. Electrostatic desalting, which is used to prepare crudes for the CDU, often requires additional techniques that remove contaminants that cause fouling. Additives may be applied at several stages of the refining process as needed. Additives added to crude entering refinery tanks are surfactants for pretreating, asphaltene stabilizers, solvents and surfactants to prevent sludge deposition, hydrogen sulfide scavengers, etc. Additives for emulsion breaking, solids conditioning and wetting agents, contaminant removal, fouling control, etc. are added in treating, desalting, and preheating systems. Finally, additives for corrosion inhibition, contaminant removal, fouling control, wastewater treatment, etc. may be added throughout the refinery. Such additives can be vital in processing troublesome crudes. Companies that supply chemical additives often promote the potential benefits of chemical additive programs, such as those that remove metals and other contaminants from refinery feed streams, improve desalter efficiency, reduce the burden of desalter effluent water treatment, and limit downstream fouling and corrosion, among other benefits. The table summarizes the solutions chemical additives provide, and the resultant benefits for the refinery. As mentioned previously, refiners can potentially reduce problems with fouling by using chemical additives. Here is a non-inclusive list of companies that supply refiners with such chemical additives. Here is our sponsor's experience. In order to properly engineer a lifespan fouling control program, Baker Hughes, a GE company, begins with a fouling root cause analysis to identify the source of fouling, the mechanism of fouling and solutions, both operational and chemical, to mitigate fouling. This analysis incorporates a detailed unit survey to understand the fouling history and operational impacts on the unit. Analyzing the deposit that has formed in the unit reveals the source of the fouling problem. Such analyses can quantify inorganic salts, inorganic corrosion products, or identify the functionality of the organic foulant that has contributed to the deposit. Feed characterization is a tool to help identify the mechanism that is causing the fouling. A typical approach is to characterize the feeds analytically by a specific set of compositional parameters known to indicate fouling potential. Fouling mechanisms are determined by which parameters exceed concern levels. In addition to the deposit and feed characterization work, proprietary fouling studies can also be completed on the feed streams to various units to evaluate the performance of antifoulants and guide the development of appropriate treatment strategies. Multiple companies offer tests, systems, software, simulators, and other services and products that help refiners possibly predict and reduce fouling. Here is a non-inclusive list of such offerings. Additional information on these companies' technologies can be found in our just published strategic report entitled Novel Strategies of Processing Price-Advantaged Crudes in a Volatile Oil Market. Here is our sponsor's experience. The Lifespan Exchanger Fouling Control Program is designed to minimize problems within refinery heat exchanger systems, maximizing run time, applicable for crude units, hydrotreaters, FCCUs and other miscellaneous heat exchanger systems and reboilers. The complete program encompasses root cause analyses, proprietary testing used to recommend fit-for-purpose treatment solutions, critical monitoring of the system and achievement of performance goals. The Lifespan program is an integrated package of engineering and chemical tools used to develop customized fouling control programs, specific to each refiner's requirements. In addition, the Field as It Services technology assists refineries in understanding the blending impact of various crude oils being processed or considered due to asphaltene destabilization and agglomeration. Our technical specialists carefully evaluate the operational data and test results to ensure we have a complete picture of the fouling process. From the evaluation, appropriate antifoulant products are screened for their effectiveness and recommendations are developed to solve the fouling problem in the most cost-effective manner possible. BHGE have developed a series of monitoring tools over the past few years for fouling control applications. These tools range from basic operational data trending to detailed heat transfer calculations. Monitoring of the unit allows assessment of the rate of fouling and the effectiveness of the treatment program. Refiners must be vigilant of the potential of fouling issues when processing crudes. Refiners should know the individual crude properties, blend recipes, contaminants, and practices that can result in fouling. Fouling in the refinery may ultimately eliminate the benefits of sourcing inexpensive crudes and blending to save money. In the refinery, because the desalter plays a critical role in minimizing fouling, refiners need to ensure that this unit is suitable to handle the incoming crude. Chemical additives available on the market may be helpful in reducing fouling. Antifoulants available on the market can perform multiple functions, namely as dispersants, corrosion inhibitors, scale inhibitors, metal deactivators, and antioxidants. Refiners can also turn to commercial instrumentation and testing methods to detect and prevent fouling. Therefore, it is up to individual refiners to customize solutions to resolve specific fouling problems. Thank you very much for watching our video. Join us in January for the second part of the series, video number 7, A Lot of Problems, Fouling and Corrosion, Part 2, Corrosion. Thank you to Baker Hughes GE and Dorf Katal for sponsoring this video. Sponsorship opportunities are still available for the rest of the seminar series. Please contact Matt Wonder at mwonder@hydrocarbonpublishing.com to sponsor a future video. Sign up today to receive our quarterly technology newsletter, Worldwide Refinery Processing Review. Since it was launched in 1998, The review has become the most authoritative and comprehensive publication of the latest refining technologies around the world. The review monitors commercial technology developments and competition, plant operation improvements and troubleshooting, and R&D trends for all processing units, from the front end to the back end, in a single source. Each issue covers 2 technology topics with the following sections: market and technology trends and opportunities, state-of-the-art technology, plant operations and practices, refining R&D alert, worldwide installed capacity, recent construction activity and completed construction projects, latest refining technology developments and licensing. As shown in the table, this year's subscription will cover 8 topics, 2 in each quarter. Apart from an annual subscription of the review, individual quarterly issues and individual technology topics are also available for purchase. For more information, contact us at review@hydrocarbonpublishing.com. Here are upcoming crude oil quality events. Your comments are appreciated. Please send your comments to info@opportunitycrudes.com so we can enhance the value of upcoming seminars. Disclaimers.